So this week we're going to talk about chapter 5 and 6. It's about sampling and types of distributions. I used to have some pretty difficult questions on these, but I've really scaled it back to try to just get the underlying concepts of about samplings and the distribution types without a lot of quantitative questions, and really just focusing on what's the real important part you should be drawing from. But I'm still going to go over a lot of the main points and kind of the qualitative knowledge you need to know and understand for the future chapters that we're going to talk about, especially when we get into hypothesis testing, which I believe starts next week. But anyhow, by now, after a steady diet of coins, dice, and abstract ideas, you may be wondering, what does all this statistical equipment we've been building have to do with the real world? Well, now we're finally going to start getting into it. So in this chapter, we begin looking at the real business of statistics, which is, after all, to save people time and money. People hate to waste time doing unnecessary work, and one thing statisticians can do is tell us exactly how lazy we can afford to be, or how to lie around with statistics. There's a lot of other interesting directions we could take this about, the use of statistics to lie, but anyhow. So the problem with the world is that the collections of stuff in it are so large, it's hard to get the information we want. Basically, what it's saying is, we're never going to be able to survey an entire population to find the true answer. So what we want to do is, take a sample and get a good estimate of what that might be. Things that we do this for are like voting population, what percentage favors each candidate for, the likelihood of the presidential election, right? Like, is it going to be the Democratic or the Republican nominee most likely to win based on a poll? And then, it also depends on who's doing the poll. Is it a liberal network or a conservative network? And they may be, adding bias in to, get better ratings. Other things would be, quality controls, such as what is manufactured goods, like what's the defect rate. So you have, an assembly line that's creating light bulbs. What's the rate or the percentage of light bulbs that won't actually work by the time they get to somebody's house from the factory. And then finally, an interesting example, pickles, what's their average length? So the pickle jar makers need to know. Also, another kind of quality control issue, is it going to fit in the jar? And, most people want all their pickles to be roughly the same size. So, the industrious, hardworking, simple-minded, beaver-like way to answer these questions would be to measure every single pickle in the world, which would be nearly impossible, and do some arithmetic. Let's find what is the longest pickle, and that's how we need to make all of our jars. But we aren't beavers. We're statisticians. We're looking for an easy way out. Like, what's the easiest way we could try to solve this problem without having to actually measure every cucumber that's going to be made into a pickle? Anyways, Beaver eats the pencil anyways. Don't ever ask him to do your math for you. So our method is to take a sample, a relatively small subset of the total population, the way pollsters do at election time. So question 1, how do you feel about polling? So I don't know about this guy. He looks kind of creepy to me, but he's got a pie. I don't know what he's going to do with it. So an obvious question is, how big a sample do we have to take to get meaningful results? Well, greater than 1 probably. There's something called power tests and other things we can do to really determine, based on what is the population size, what is the minimum sample we could need to survey or utilize in order to get statistically relevant results. Check something real quick. Recording. Got that. Okay. So, and the answer to that minimum sample size, or what you should inscribe in your brain forevermore, will turn out to be, if n is the number of items in a sample or the sample size, then everything is governed by 1 over the square root of n. So that's how we kind of compensate for the fact that we're taking a sample. So you'll see several formulas coming up where the population parameter that we look at, all we have to do is adjust it by this 1 over square root of n, and that's how we compensate with the fact that we took a sample and we didn't actually get the true mean. We got a mean based on a sample or whatever we're looking for. So governed by 1 over square root of n. I didn't even know that was on the ballot. So, sampling design. Not sampler design. I don't know if there's anybody who knits or does quilting, but that's kind of where that joke comes from. But before doing the numbers, we should point out that the quality of the sample is as important as it is its size. So how do we assure ourselves that we're choosing a representative sample? How do we avoid bias? So the selection process itself is critical. For example, a voter survey that systematically excluded Black people would be worthless. And there are a host of other ways to run or bias a sample. So I mean, if we eliminate an entire demographic group, then obviously that sample is flawed and we're not going to get accurate results. So not to prolong the mystery, the way to get statistically dependable results is to choose the sample at random. So I guess we're talking about sample. So the simple random sample is, pivotal or an assumption of all statistical tests that we're going to talk about in this class. Unless we get, well, we're not going to get to non-parametric, but all parametric statistics, one assumption is that the sample was drawn from a simple random sample. So what is that? So suppose we have a large population of objects and a procedure for selecting n of them if the procedure ensures that all possible samples of n objects are equally likely. Then we call the procedure a simple random sample. So every person or in a particular group, let's say classroom, has an equally likely chance of being selected to be in our sample. So let's say there's 30 students in a class and we want to select 5 at random. Each student has an equally likely, identically, independently distributed chance of getting selected. And that's how we maintain a simple random sample. The simple random sample has 2 properties that make it the standard against which we measure all other methods. First, it's unbiased. So each unit has the same chance of being chosen. And the second is independence. Selection of one unit has no influence on the selection of other units. So because person 1 got selected doesn't mean it has no influence on any of the other people in the classroom that might get selected. So there's more to that assumption too, but basically we're ensuring that it's not biased and that all the samples that we select are independent of each other. So it's not like the probability that we talked about previously that, selection of this is conditional on that, rolling the 2 dice example that we did last week. So that does not help with independence. Unfortunately, in the real world, completely unbiased independent samples are hard to find. For instance, surveying voters by randomly dialing telephone numbers is biased. It ignores voters without a telephone and oversamples people with more than one number. So, especially if you're basing it on people with house phone numbers instead of cell phones. Most people don't even have house phones anymore, so that would really bias it. You'd be stuck with only the people that have house phones. So it's theoretically possible to get a random sample by building a sampling frame, which is a list of every unit in the population. So let's say you had a phone book, if those even still exist, with everybody's phone number in it, and you were to just randomly take numbers out of that phone book. Or we could put all the names of cards of people and pull n of them out of a drum. So kind of like, an old lottery or bingo style way of selecting random numbers or random people. But this is not always easy. Making the frame may be prohibitively costly, controversial, or even impossible. For example, an EPA water quality study needed a sampling frame of lakes in the US, so then somebody has to decide what wet spot is a lake. Well, are there other ways to sample that are more efficient and cost effective than a simple random sample? Yes. If you already know something about the population, for instance, you do a stratified random sample. So stratified, you divide the population units into homogeneous groups called strata and draw a simple random sample from each of those groups. So that way, each group has the same sample size in it. So in this example of different kinds of pickles, you'd have different strata of pickles: garlic dills, pickled red peppers, kosher dills, gherkins, relish. So each different kinds of pickles, and then we take, let's say, 20 of each of those, and then we could, do some kind of comparison on them. Another kind of sampling technique is called a cluster. Sampling groups the population into small clusters, draws a simple random sample of clusters, and observes everything in the sample cluster. This can be cost effective if travel cost between randomly sampled units is high. So clustering samples, trying to think of other reasons you might use clustering. Well, an example for here is a city housing survey, which divides a city into blocks, randomly samples the blocks, and looks at every housing unit in each of those sampled blocks. In more advanced statistical modeling and machine learning, when we get to clustering, there's reasons to look at clustering differently, but at this kind of intro to statistics, we won't get into it. Systematic is another kind of sampling technique. Starts with a randomly chosen unit and then selects every kth unit thereafter. So if you're looking for every 10th mailbox in order to put, a random flyer in. For instance, a highway traffic study might check every 100th car at a toll booth. This plan is easy to implement and can be more efficient if traffic patterns vary smoothly over time. Word of warning, or first possible violation of assumption. Most statistical methods depend on the independence and lack of bias of simple random sample. The results ahead apply to the simple random sample only. For other sampling procedures, the results must be modified. The details appear in specialized sampling textbooks and computer algorithms. So basically what I was saying before, all the tests we're going to learn in this class in the future all depend on the sample that we're working with was drawn from a simple random sample. Second, without randomized design, there can be no dependable statistical analysis. So no matter how it is modified, the beauty of random sampling is that it statistically guarantees the accuracy of the survey. So if you don't use a simple random sample or a sample that's not, a random sample, then you've introduced bias, and then any statistical test you try to run on it will be flawed. Which is not saying that that doesn't happen. It happens a lot, especially with regard to media. So, commonly used method, especially prone to bias, is called an opportunity or convenience sample. So, if I was, trying to understand everybody's favorite color in Jacksonville, but then I only sampled the students in my class, that would be a convenience sample because it's an easy audience to get a hold of. So, and avoiding all the bother of designing a procedure, the opportunity sampler just grabs the first in-population units that come along. So that introduces an obvious kind of bias. The classic example is Sheer Height's book, Women in Love. 100,000 questionnaires went to women's organization, an opportunity sample. Only 4.5% were filled out in return, response bias. So our results were based on a sample of women who are highly motivated to answer the survey's question for whatever reason. So sample size and standard error. So we'll talk about how you have to adjust the standard deviation to the standard error by compensating for that sample size. So now let's get down to brass tacks. Real brass tacks, that is. Suppose the Bernoulli tack factory is churning out brass tacks, some of which inevitably are defective. The astute reader will recognize this as a Bernoulli system. Each new tack is the outcome of a Bernoulli trial with some probability p of success being defect-free and some probability of 1 minus p of failure being defective. So we think of this situation as if there were a hidden but real Bernoulli machine whose probability p governs the outcomes we observe in the so-called real world. Since the Bernoulli machine is invisible, we don't know what p is, but we'd like to find out, so we take a random sample of n tacks and find that x of them are okay. So we've taken our sample of tacks. Now the proportion of successes in the sample should be somewhere around p, so we call it p hat. P hat is equal to our proportion of x that we found divided by the sample size n. The p hat is the number of successes x in the sample divided by the sample size n. For example, if p was 0.85 and we sampled n equals 1,000, tax, maybe we found x equals 832 good ones, making p hat equal to 0.832. So 83% not defective. Well, how good is that estimate? And we answer with another question. What does the first question mean? So we can't know the precise difference between p hat, our estimate, and the true population parameter p. So because we don't know the value of p, the real question is this: if we took many samples of 1,000 tax and observed p hat for each sample, how would those values of p hat be distributed around the true value of p? In fact, these p hat values are looking more and more like a random variable that we talked about last week. So the selection of the n-unit sample is a random experiment, and the observation p hat is a numerical outcome. So to be precise, if x is the number of successes in the sample, then x is nothing but our old friend, the binomial random variable. In trials, probability p, and we define the observed proportion to be the random variable p hat is equal to x divided by n, or sample size. So knowing all about x, we quickly conclude a few facts about p hat. The mean of p hat is the expectation of p hat should be equal to p. So the average p hat value should be equal to our true population parameter p, or the proportion of successful trials. So the standard deviation of p hat is, or sigma of p hat, the square root of p times 1 minus p divided by the square root of n. So you'll see in this formula, this was for, finding the standard deviation of a population. And if you put 1 over the square root of n times that, you can see that now we've compensated for the sample size by adding that figure that we talked about earlier in this presentation. And thus, for large n, p hat is approximately normal. So it comes back to the law of large numbers and the central limit theorem. And there you have it. All the observed values of p hat will be centered around p, not surprisingly, and their standard deviation, or spread, is proportional to the magic number we mentioned at the beginning of the chapter. It depends only on sample size, not on population size. And since p hat is nearly normal, we can use our rule of thumb to conclude that approximately 68% of all estimates will fall within one standard deviation of the true value of p. Going back to the tax, with n equals 1,000 and p equals 0.85, we get standard deviation of, or the standard deviation of p hat is 0.85 times 0.15 divided by 1,000. You take the square root, and that gives us a spread, or a standard deviation, of 0.0113. So we expect about 68% of our estimates to fall in the narrow interval between 0.8387 and 0.8613. So what that standard deviation is. So that would be one standard deviation from mean. Standard deviation of p hat is a measure of the sampling error. So as we've seen for the binomial p hat, the sampling error is inversely proportional to the square root of n. Increasing the sample size by a factor of 4 reduces the spread, or sigma p hat, by a factor of 2. So already at n equals 100, you see that the sigma of p hat, or standard deviation of p hat, is down to 3.5%. So if we look at the different sample sizes for comparing these two proportions, as we increase the sample size, you can see that we go from, this number is way off, 0.357. That would give you that would even be outside the bounds of probability, right? But as we increase the sample size, we get to 10,000, we can see that our likelihood of being within one standard deviation of the true population mean is within 0.0036. That's the likelihood of being less than % off, right? So that's kind of demonstrates the law of large numbers. So the larger the sample size, the more accurate our statistical tests and values will be. But four-step process in statistics. So we find population with unknown parameter. So for Bernoulli tax, we have some true amount of defective tax. We're interested in this proportion. Find an estimator. That's theoretical sampling distribution and standard deviation p hat. Then we find, what's the standard deviation of, or basically how good is our estimate, or how far likely is it within the true population parameter that we're interested in. And that goes for all hypothesis testing, etc., that we're going to get to. Actually, draw a random sample and find the estimate. P hat is exactly 0.84. So report the result in a statistical or sampling error. So we have P hat equals 0.84 with a sampling error of 1.1%. Sampling distribution of the mean. Now we move from brass tacks to dill pickles. That is one mean pickle. Slightly above the mean, actually. That was a big ass pickle. So jar manufacturer would like to know the average length of a pickle without examining every cucumber in California. So they randomly select n pickles and measure their lengths. You have, the first pickle is x1, the second pickle is x2, all the way to the nth pickle is xn. So by now you may be used to the idea that each x sub I is a random variable and the numerical outcome of a random experiment. So if mu is the unknown mean pickle length and sigma is the standard deviation of the pickle length distribution, then the expectation of x sub I is equal to the mean, or mu, the parameter or population parameter or mean, and sigma of xi is equal to sigma of population, or the sample standard deviation should be fairly equivalent to the population standard deviation. So for every I, because xi could have been the length of any pickle. Now we look at the sample mean, the average length of the selected pickles. It's a new random variable given. We take each of our x's and we divide by our total sample size, and we get our x bar, which is our sample mean. As far, we'd like to know how close this is to the true population mean mu, meaning if the sampling were done many times, what's the distribution of x bar? Because we know about x1 through xn, we also know that the expectation of x bar should be equal to the mean, the true population mean, and the standard deviation of x bar should be equal to the true population standard deviation times 1 over the square root of n, or divided by 1 square root of n, which compensates for our sample size. So once again, we see the magical denominator, the spread of observed sample means goes as 1 over the square root of n. We don't know the shape of x's distribution. The sample probability distribution p hat was almost normal because it was based on a binomial random variable. But what about x bar, the sample mean estimator? Turns out that x bar is also approximately normal. This famous result is called the central limit theorem. Very important to statistics, and in fact, none of our statistical tests that we learn about would work without this particular theorem. It says if one takes random samples of size n from a population of mean mu and standard deviation sigma, then as n gets large, x bar approaches the normal distribution with mean mu and standard deviation sigma divided by the square root of n. So then we have a probability that x bar is somewhere between a and b, and we find that with these formulas. We get a z-score, which we're going to talk about, is that value with respect to a normal curve. So talked previously about things being normal and bell-shaped curves, so you'll start to see why it's important. So what is remarkable about this is that regardless of the shape of the original distribution, in this case, pickle lengths, the taking of averages results in a normal distribution. To find the distribution of x bar, we need to know only the population mean and standard deviation. So the three probability densities above all have the same mean and standard deviation, despite their different shapes. when n equals 10, the sampling distributions of the mean x identical. So what's that saying is it doesn't really matter what the underlying distribution was. Due to the way we're taking samples, we take a sample from here, we took 10, and this is the distribution we got. We took 10 samples from this distribution, this is the distribution we got. Take this kind of skewed, almost looks like a chi-square distribution. We took 10 samples from this, and we see, look, it's as the whole reason statistics works is because of the central limit theorem that we just talked about, and that kind of law that occurs due to sampling. And when we take it from basically all distributions when sampled converge to the normal distribution, and that's why statistics works. So another important distribution is the t distribution. Amazing as the central limit there is, it has at least two problems. One, it depends on a large sample size. It comes back to that law of large numbers. Remember when I said, sample size of 10,000, the error is so small, 0.003 or whatever. Second, to use it, we need to know the standard deviation. So you can see how that can be kind of a pitfall, right? If we don't have a large sample size and we don't know the standard deviation, we don't know how approximate we are to a normal distribution. So this guy with the last name of Student developed this student t distribution for small sample sizes, and which is good because sample sizes are often small, and knowing the true population parameter of sigma, or the standard deviation, is usually unknown. Certainly in the case of pickles, we have no idea how widely their lengths vary around the average. What we can do in this case is to estimate sigma by taking the standard deviation of the sample, which you'll recall is given by the formula s equals 1 over n minus 1 times the sum of each of our x values subtracted from x bar the average squared. So that's how you get standard deviation. And in place of the random variable, we subtract it from the mean, and basically this gives us a z-score. So what we do for a t-score is we substitute s for a sigma, and we define a new random variable t by t x bar minus mu with the sample of, or the standard deviation divided by the square root of n. So in this case, for large sample sizes, we use this formula, and we draw it from a z-table, and from smaller sample sizes, basically under 30, we would use a t-table. So this is what the normal distribution looks like. Population density, you can see, we said earlier, 68% roughly would be within one standard deviation. 95 should be within two standard deviations. 99% should be within 3 standard deviations. And once you go beyond that, it's so minuscule. But usually, for most of our statistical tests, we're going to be very interested in, is it within 2 standard deviations, or 95%? So we'll talk about 95% confidence intervals. We'll talk about alpha of 0.05, which is really 1 minus 0.95. So an alpha of 0.05 is equivalent to 95%. So all these numbers will come back and haunt you. So what you'll notice, this line is the normal distribution. As we increase the sample size in a student's t distribution, we approach the normal distribution. In fact, by the time we get to sample size 30, we're pretty much just mimicking the normal distribution. But at lower sample sizes, we need to take into account that the distribution is a little bit different, and it'll change how we answer certain questions when we get into inferential statistics. So, t is more spread out than z. It's flatter than normal. This is because the use of s introduces more uncertainty, making t sloppier than z, I guess is a good way to put it. So the amount of spread depends on the sample size. The greater the sample size, the more confident we can be that s is near sigma. And the closer t gets to z, the normal. So a couple other distributions I wanted to bring up. This is called the F distribution. You can see it's very much skewed, and we're interested in this tail over here. When we get into analysis of variance later in this class, ANOVA is another name for it. It's based off of this particular F distribution. The chi-square distribution looks very similar, but it's slightly off from the F distribution. Chi-squared function or distribution comes into when we're looking at contingency tables, and we're looking at possibly two qualitative variables and trying to compare them, but also looking at two groups. Say you're trying to compare male and female, and you want to do a chi-squared test, then you're going to pull off this distribution. So those are all kind of examples of times when you're not going to pull from the normal distribution, but we just need to, while we're talking about distributions, we need to bring these up because they're going to come up in tests that we're going to run later. So this is the Poisson distribution. You'll probably need to know this distribution for operations management or quantitative business methods, because if you look at inter-arrival times in simulation, it's based on this distribution. But that's the only thing I want to say about that. This lambda is like inter-arrival rate. So probably not going to see this again in my class, but in other classes you take, you'll probably. So let's kind of check back. So we talked about mean, mu as a parameter for the population. We have a statistic x bar. If we're talking about proportions, p is some proportion that's the true value of that population. And we use p hat as an estimate or a point estimator. Standard deviation, we use sigma, and we use S for the statistic. Correlation, I'm not sure we've talked about it yet. We'll talk about that in the future. Rho is the true, correlation between two variables, and we use R for Pearson's R, but we'll talk more about that when we get into linear regression. Right, so that kind of talks about sampling and distributions. So let's talk about confidence intervals and get on. We can do some cool stuff in Excel with that. I built a calculator that will help with using the confidence interval function. So in the last chapter, we looked at sampling, starting with a large population. We imagined taking many samples, and we deduced how some sample estimators were distributed. In this chapter, we do the reverse. Given one sample, we ask the question, what was the random system that generated its statistics? So that is, given a single box of tax and the results of the last chapter, what can we conclude? So this shift represents a change in our mode of thinking from deductive reasoning to induction or inductive reasoning. So it's like Sherlock Holmes. In deductive reasoning, we reason from a hypothesis to a conclusion. If Lord Fastback committed murder, then he would wipe the fingerprints off the gun. Inductive reasoning, by contrast, argues backward from a set of observations to a reasonable hypothesis. So Lord Fastback's monogram on the handkerchief and this gun Fastback is the murderer. Watson, I'm 95% certain. So in many ways, science, including statistics, is like detective work. Beginning with a set of observations, we ask what can be said about the systems that generated them. How do we estimate confidence intervals? So it's one of the most effective forms of statistical inference, and one you see every day before election time. So in a recent election somewhere, incumbent Senator Astute, accent on the last syllable please, commissioned a poll by Better Holmes Research. Pollster Holmes draws a simple random sample of 1,000 voters and asks them what they think of Astute. He's God's gift to humanity, or he's the deity's special blessing on most of humanity. After censoring the remarks of a few grumpy outliers, Holmes finds that 550 voters favor his client, Senator Astute. This is the single observation. So we have a p hat of 0.55 or 55% out of the 1,000. So you only asked 1,000 people, but there are 1 million voters in this state. I don't care if there are 1 million or 1 billion. Made a simple random sample. This means they can offer you an ironclad guarantee. This guarantee, it's an absolute money back type, right? Well, statistically, actually. Yes, I can say that 95% confidence that the true population proportion P is between 0.519 and 0.581. So either way, it's greater than 50%, right? 51, almost 52% at the minimum of that confidence interval. 95% certain, what do you suppose would happen if I ran on a platform of 95% honesty? I don't know. It's never been tried. So after a student calms down, Holmes explains what he means by 95% confidence. He knows that his estimation procedures has a 95% probability of producing an interval containing the true value P in his many years of polling. P has fallen within the confidence interval around the observed value 95% of the time. So Senator is still confused. So Holmes gives him an archery lesson. Shoot, anything to take my mind off these statistics. So consider an archer pollster shooting at a target. Suppose that he hits the 10 centimeter radius bullseye 95% of the time. That is only one arrow out of 20 misses. So sitting behind the target is a brave detective who can't see the bull's eye. The archer shoots a single arrow. Knowing the archer's skill level, the detective draws a circle with 10 centimeter radius around the arrow. He knows that 95% confidence that his circle includes the center of the bullseye. He reasoned that if he drew 10 centimeter radius circles around many arrows, his circles would include the center 95% of the time. So the true center here, and then the X's, the actual arrows, and all the circles. So probabilists use this term stochastic as a random process to describe random models. It's derived from the Greek stochastes tai, meaning to aim at a target, or guess from stokos, a target. But basically what it's saying is if you took many samples and many confidence intervals, 95% of the time it would contain the true population parameter. So Holmes now needs to translate the archer lesson into the language we developed last chapter. Step 1, shoot a lot of arrows. So probability calculation finds the width of the bullseye. The estimate p hat are our arrows. We saw that the sampling distribution of p hat is nearly normal with mean p and standard deviation. So this is the same sigma that we talked about last week. So P is the bullseye center, right? That's the true population parameter. Since the curve is normal, so it's drawn from a normal distribution, right? We use the Z transform and a standard table to find the width of the interval within which 95% of the arrows hit. We'll see exactly how to do this in the next few pages. Find this width to be 1.96 standard deviations. So this is a very important number. 1.96 is the Z-score that corresponds to 95% confidence. So a very important number to remember. So the radius of the bullseye is 1.96 standard deviations. 95% of arrows land within that interval. Now we do some algebra. By definition of the Z transform, 0.95 is approximate to the probability of the difference from our p hat to the true population probability, or proportion, and divided by sigma of that, or the standard deviation of that. So I calculate all that out, and we know that in a confidence interval, the p hat that we sampled is somewhere between 1.96 times the standard deviation of p from the true population. So it's just another way of saying that 95% of the p hat arrows land between p minus 1.96 times the standard deviation of p and p plus 1.96 times the standard deviation of p. Now we're in the position to view the target from behind. One more turn of the algebra crank makes it this value. So here we are drawing circles around a lot of arrows. An example, making intervals around p hat and saying that 95% of them cover p. But there's one tiny problem. We don't actually know the size of the bullseye because we don't know p, and the width is a multiple of, the spread or the standard deviation about p. So the circles are all different sizes now, but it's okay really. So we fudge a little and use the standard error of p hat. So the standard error, we compensate for the sampling that we did. So we come back to that 1 over the square root of n. And that compensation turns our standard deviation into a standard error, which will be slightly more accurate. So we put that in its place. It's close enough. It's the best we can do, and it can even be theoretically justified. So now the formula is here, and instead using the standard error, we can compensate for whatever sample size. And the more sample that we have, the more accurate our results would be. So again, this equation describes the probability that the true fixed population proportion falls within the random interval. If we sampled repeatedly, these intervals would cover p 95% of the time. So now our probability calculation done, and it's time for step 2. Detective work. In a real poll, Holmes takes just one simple random sample of 1,000 votes, finds p hat equals 0.550, 55%, and wants to infer p. He makes use of step 1 to compute the standard error is 0.0157. He concludes that we can have 95% confidence that p is within the range, 1.96, which corresponds to the 95% confidence interval, times the standard error, plus or minus the p hat. So we would get a confidence interval that is 0.550 minus 0.031 and 0.550 plus 0.031. And we would say that 95% of the time there should be the true value of p in that range. This is what polls mean when they refer to their margin of error. In this case, Holmes found that 0.519 to 0.581, in other words, that 55% with a 3% margin of error, polls typically use 95% confidence level. So next time you're reading, statistics and news or whatnot, you can have a better understanding of how they may have come about that number. And knowing the margin of error could drastically change how far off that is. Although 95% confidence is good enough for newspaper polls, it is not good enough for Senator Astute. He wants 99%. So anything less than my big money people won't invest. Contribute to my fight for liberty and justice. So how to increase confidence? For using the archery target, we can see two ways. One is to increase the size of the circle you draw, right? So, if we increase it to where, 99% or 100% chance that the true value of p is there. Another would be to improve the aim of the archer in the first place. So her arrows land closer to the bullseye. First method is equivalent to widening the confidence interval. So the greater the margin of error, the more certain you are the true value of p is in the interval. I'm 100% confident that p is between 0 and 1, right? It's got to be between those two numbers. So maybe it's time to see exactly how we find ends of these confidence intervals. For the relevant number, here we usually call alpha. It measures the difference between the desired confidence level and the certainty. For example, when the confidence level is 95% or 0.95, alpha is 0.05, like I said earlier. So we speak of the 1 minus alpha, 100% confidence level. So finding the 1 minus alpha, 100% confidence interval, means look at its standard normal curve and find the points plus or minus z between which the area 1 minus alpha. So in this case, it was 0.95, but if we wanted to increase that to 0.99, then we'd be interested in alpha of 0.01. So this point is called z alpha 2, is the z value beyond which the area is 0.025 equals alpha divided by 2. So we divide alpha by 2 if we're looking at a one-tailed test, and the value alpha kind of assumes that it's a two-tailed test. So we're interested if a particular critical value is in either tail, we use the full 0.05. But if we're only looking at a right-tailed test, then we're looking at alpha divided by 2. So that'll come into more importance coming up when we start doing hypothesis testing. So we can find z alpha 2 straight from the standard normal table. I'm going to show you how to do it in Excel, so you don't have to look it up. So let's say we have a one-tailed test, then we're going to look at alpha divided by 2. You can look it up on a table, but we'll look at, we'll use a formula that will do it for us. So let's say you have an interest for z alpha divided by 2, so a one-tailed test for alpha of 0.06. So I've posted an Excel spreadsheet, but you can see if we put in 0.06, so whatever alpha we're given, we want to find the z value for alpha divided by 2. So the first thing we need to do is have a formula that divides our alpha by 2. And then to get that z alpha 2, we need to use the norm's inverse. So basically what that formula does is it looks at the normal curve and finds the inverse of it and of our B5. So it's going to look up 0.03 since it's z alpha 2. And then I put the round formula on it so it'll round it to 2 decimals. So the z-score for alpha equals 0.06 for a one-tailed test is negative 1.88. Important to know, because if we were looking at a 94% confidence interval, then this is the value we want to use. So here's a little table of critical values for various levels. These are all very important numbers, and if you memorize these, it'll make your homework easier, so you don't have to keep looking them up. So for a 99% confidence interval, the z-score is 2.58. For a 95% confidence interval, it's 1.96. We already saw that one. For a 90, it's 1.64. For 80, it's 1.28. I don't see that one as often, but these three you will see a lot. So I'm remembering these numbers 1.64, 1.96, and 2.58 will be very good to memorize and to know in the future, or at least write them down when you're doing your homework so you can quick reference them. So to make a 99% confidence interval, we use that table to write 0.99, so which we sloppily abbreviate. So now we know, we're pulling from that table, that instead of 1.96, we're going to multiply 2.58 times that standard error. So we multiply that out. So to get a 99% confidence interval, well, we already knew what the p-hat was. Now we're going to add or subtract 0.041. So still between, 0.51 and 0.59, right? So that's 99% confident that it's in that. So we kind of widened it, right? But it still makes him happy, right? Because he's still more than 50% chance of being reelected. All right, so let's look at another example. So a random sample of n measurements was selected from a population with an unknown mean, mu, and a known standard deviation. So calculate a 90% confidence interval for mu. So we have a sample size of 50. We have x equals 26 and a variance of 15. So for a second example, what we're interested in, 90% confident. So you put 0.9 for 90%. It'll calculate your alpha for you. So it's an alpha of 0.1. Sample size was 50, right? So put the sample size in. The x of interest, 26. Put that in. The variance, 15. Well, we need to, if you're given the variance, then we need to take the square root of the variance. So that's what this formula does. Take the square root of the variance to get the standard deviation. Now, there's this formula that finds the confidence level. So it finds the number that's going to be plus or minus. So it's going to take into account and look up for you the, the 1.96 or the 1.64 in this case. It's by looking up what that confidence level is. It's going to take the square root of B5 for the variance. You may have to adjust that if you are given a standard deviation instead of a variance. So we got 1 minus B1. So for the alpha, we got our sample size in there. So it's going to compensate for that. Basically, we put all these important variables into our confidence function, and it's going to give us a calculation. So down here, all I've done is take this confidence number plus or minus this number from our x value to get our confidence. So we got our lower bound and our upper bound of our confidence level. So small calculator to help you calculate a confidence interval. So widening the interval is one way to increase our confidence in the result. As we mentioned, another way would be to shoot our arrows more accurately. If we knew that the archer got 95% of our arrows within 1 centimeter of the bullseye, our estimates could be a lot sharper. How do we do this? By increasing the sample size. So the width of the confidence interval depends on the sample size. So you know it was dependent on the sample. So the more sample, the more accurate our estimations can be. So E is the error given by this. So the bigger we make n, the smaller the error. Makes sense, right? So quadrupling n halves the interval's width. So the larger the sample size, the tighter our confidence interval can be. Astute asks Holmes to give him a small error with high confidence, say 99% confidence with an error rate of plus or minus 0.01. Holmes solves for n then. So that's how we can get sample size, right? So where P star is a guess at the true proportion P. Remember, we haven't taken the sample yet. So we gotta get out our wallet, right? Because you're gonna have to pay for some surveys. But taking a conservative guess of P star equals 0.5, Holmes finds that at 99%, so the 2.58 comes from the Z table for 99%. We're saying just a rough, what's a 50-50 chance? And we want an error rate of no more than 0.01. So we calculate all of that out and we find that we need a sample size of 16,641 in order to fulfill the request to be 99% confidence interval with an error rate of only 0.01. So 1,000 voters gave a 3% chance. To get a 1%, we'd have to go all the way up to 16,641, which was a significant increase, right, on the number of people that need to be sampled. So on the other hand, who can place a value on peace of mind? So they do the poll and go into the election with 99% confidence. But all this probability stuff is only good before an election. After the election, the senator is either 100% in or 100% out. Despite everything, Senator Astute loses the election. So confidence intervals from mu. Up to now, we've been looking at confidence intervals for proportion P of a population, exactly the same. Reasoning works for the population mean mu. So instead of using proportion, we're going to look at a mean value x bar. So in the last chapter, we saw that the distribution of sample means x bar is approximately normal, centered on the actual population mean mu, with standard deviation sigma divided by the square root of n, where the standard deviation is the population standard deviation. So we want to find that z value, which happens to be, value negative 1.96 on either side. And again, not knowing sigma, we replace it with the standard deviation, or the standard error. So the term S divided by the square root of n is called the sample standard error, and written SC of x bar. So that will help us compensate for our sample size, and obviously the larger the sample size, the lower the standard error or error rate will be. So just as before, we have found that the random interval about x bar, or our sample mean, will be for 95%, 1.96 times the sample error times our x bar. So covers the true mean, mu, with probability 0.95. So now we can call in Sherlock Holmes to make a statistical inference based on a single sample of size n with mean x bar. So and we are 95% confident that the mean mu is within the interval as stated. As before, for arbitrary level of confidence 1 minus alpha, we replace that'll be alpha 0.05, 1.96 by z alpha 2. So we know that these tails would be 0.025 and 0.025. So to summarize, for a simple random sample of large size, the 1 minus alpha times 100% confidence interval is basically what we've been saying. It's we know that the true population mean mu is somewhere in between, or on either, in between the interval of the standard error times the z-score plus or minus x bar, similar to what we did for proportions. So suppose Chameleon Motors has to crash test its cars to determine the average repair cost of a 10-mile-per-hour head-on collision. This would be really expensive, right? So they try it on just 5 chameleons. Why aren't more cars named after F-Top? I don't know, Mr. Chameleon. So they find that damage data to be 150, 400, 720, 500, and 930. So the sample mean is $540 with a standard deviation of 299. You can calculate all that out, but that's what it would be. I would just use Excel. So where can we place the mean with 95% confidence? We find our critical value. Since it's a low sample size, we have to use a t-value, right? T 0.025, 4 degrees of freedom. So for a t-test, you'll get a different t-value because it's compensating for the amount of sample that we have below 30, and it compensates for. So we plug it in, and we get 540 plus or minus 372. So the best we can say is somewhere between $168 and $912. So the company can either be satisfied or do further tests. So to compute the confidence interval using students T, we have made an unstated assumption. We assume that crash repair costs are approximately normally distributed. In example, if we crashed 1,000 chameleon cars, the histogram of repair costs would be symmetrical and mound-shaped. We cannot know this from 5 data points alone, but maybe years of experience with earlier models provide normally distributed cost histograms for front and repairs, information which would tend to support our use of students T. The last example on the last slide, researchers published a study that investigated the degree to which a country's household waste food. The researchers used data from 3,690 households. For this sample size of 3,690 households, the mean amount of food wasted is 37.2% with a standard deviation of 16.6%. So I'll leave it to you to find a 95% confidence interval for mu, true mean amount of food wasted by all households, and then compare that to an economics claim that mu is less than 36%. And then do you agree? So you should be able to use the information here, fill this out, and mimic it from the formulas on this slide. And that's what I'd like you to do. Okay.